Parents who come to Tatva often ask me, what is so different about Tatva? Because we ourselves tell them that Tatva is very different from any other school they would have experienced either themselves in their growing years or when they look around them today. And sometimes it's not so easy to help them understand what's so different. And just say 2 or 3 weeks ago, something happened which brought to my attention what really is different about Tattva. At one level, you can say what is different is very simply the way we work with our children. And the big difference is the way we work is not about teaching them things, but in everything we do, it's about enabling the wholesome development of the children's faculties. And as I was saying a couple of weeks ago, I met this beautiful example from a high school, where in the high school, the primary goal is working with the thinking faculty of the child, the blossoming of their thinking faculties when they come into adolescence. And there was this very interesting concept, you could say, in physics, in optics. And the interesting thing was when I saw this, actually, when as a teacher, I was supposed to take it to the children. And the first emotion I experienced was not joy or excitement, but actually fear. And this fear was nothing but a residue of the same fear I experienced when I met this idea when I was the age of these children in school. But then, of course, the idea is not to create fear in children, not to leave the imprint of fear in them that they carry for a lifetime, but to make every part of their educational experience, especially in the high school, a deep exploration and a process of discovery so that they truly enjoy everything that they learn. So, I thought this is a beautiful example through which you can understand what is different about Tattva. So, do enjoy the rest of this presentation, and I hope you get a very good picture of what makes Tattva special.
This video will give you a good picture of what makes Tatva so different that parents love the work we do with their children. This will involve a bit of high school physics, but we hope, especially if you're a parent of a school-aged child, that you will watch it to the end. Welcome to a world of possibility in education. As you enter, please put yourself in the shoes of a child in grade 11 or 12. This child is meeting the physics of light with prisms. The concept is measuring the refractive index of the material of a prism. This, however, is not an attempt to teach you physics or maths. Let us start by getting a grip on the basic terms. Refraction is the apparent bending of light when it crosses the interface between two optical media, for example from air to glass. The angle of incidence I is the angle made by an incident ray of light with the normal to the interface at the point where it is incident. The angle of refraction R is the angle made by the refracted or bent or deviated ray with the same normal on the other side of that interface. The refractive index mu is a measure of the extent of apparent bending that light goes through when it crosses an interface between two media. Its numerical value depends on the pair of media involved. Mu is quantified as a ratio of sin I to sin R. When mu is greater than 1, I is greater than R, and we say a ray of light bends towards the normal. When mu is less than 1, I is less than R, and we say the ray bends away from the normal. How is the value of mu determined for a given interface? It is common in a physics lab to measure mu of an air-glass interface through what is called the glass slab method. This method uses a rectangular glass slab and studies light passing through a pair of parallel air-glass and glass-air interfaces. This method starts by fixing a sheet of white paper on a board. We place a rectangular glass slab on the sheet. We fix two pins on the board vertically as shown. We look from the other side of the glass slab and position our eyes such that we can only see one pin. We now fix two pins to the board along that line of sight such that each time we can only see one pin from that side. We now trace the outline of the glass slab and remove it. We remove the pins and draw the lines as shown here. We measure I and R as shown using a protractor. The refractive index of the glass is quantified as sin I by sin R. So, what is the education being attempted now in grade 11 or 12? We now study the effect of a prism on light. The key is that in a prism, the pair of interfaces through which the light passes bending along the way, are not parallel and instead make an angle A between them. This angle is called the angle of the prism. The incident ray lands on the left interface, making an angle I with the normal to the interface at the point where the light lands, bends towards the normal as the refracted ray, making an angle R with the same normal on the other side of the interface, and then bends away from that normal as the emergent ray. Looked at another way, the light ray that would have followed the path shown by the red dashed line deviates from that path because it passes through the prism and follows the path of the green dashed line as it emerges from the prism on the other side. This deviation, represented as the angle delta between the red and green dashed lines, is called the angle of deviation. This delta has a special relationship with the angle of incidence. More specifically, delta attains a minimum value of delta min at a specific value of I given as half the sum of the angle of the prism and this delta min, while the corresponding angle of refraction is equal to half the angle of the prism. This allows us to compute the refractive index of the material of the prism as sin I by sin r, or sin of A plus delta min by 2 divided by sin of A by 2. With this background, let us now meet the conventional path adopted by most teachers in schools in taking this to children. This is most likely the path your child is following or will follow if he or she is not at a school like Tatva. So do take a close look and try to understand what it means for your child. This is the typical diagram found in the typical grade 11 or 12 textbook that a child will follow. It shows the prism, all the rays, and the key angles. Based on this figure, children are told the following. The angle of deviation delta attains a minimum value delta min at a specific value of I as shown here. The angle of refraction takes the value as given here. Based on these, the refractive index mu of the prism is computed as shown here and mentioned earlier. While the typical teacher tells us clearly, even correlating all the relevant parameters, they still only tell the child that it is so. The teacher is backed in this fully by the textbook, which is considered the infallible authority that we can and should never question. Children's task is to understand what the textbook says, not to question or challenge it. They also face negative consequences if they fail to understand it or do so poorly. Let me now contrast this approach with the other path, the path of discovery. This is the path that we at Tatva follow for all that children meet in the sciences and maths. It is a path where we do not tell the children what a concept is or explain it to them. Instead, we allow the concept to meet them in many different ways. In science, wherever possible, children experience the phenomena first and then use as much logic as is appropriate for their age to discover the concepts that the teacher is trying to bring to them. They participate deeply and actively, much like treasure hunters looking for hidden treasure. They use all the understanding and knowledge they have gathered in the past as tools in the process. In higher grades, mathematics begins to play a big role in this process of discovery in sciences like physics and chemistry. Maths, children are reminded over and over again, shows light and never lies. Every instant where maths does this only reinforces their conviction in this idea, and they begin to see mathematics as their best friend, though a most demanding taskmaster. It becomes a sort of love hate relationship. I love you because you show me truth, but I hate you because you make me work so hard. You, mathematics, are unforgiving. Let us now take the specific example and see how differently the path of discovery brings the same concept to the children and experience how it strengthens them and draws out their budding thinking faculty. If you have come this far, I urge you to participate in the same spirit as though you are a child in that class doing exactly what the children would be doing. It will be good if you can sense how you feel about it and then reflect on it as well. The first task is to understand the situation from scratch. It all begins with describing every critical aspect of the phenomenon. That blinking A in the triangle represents the angle of the prism or the angle formed between the non-parallel faces through which the light ray passes consecutively. The incident ray represented by the red arrow lands on the left face of the prism. There is a normal to the prism at the point where the incident ray lands. The ray then bends towards the normal, passes through the prism as a brown arrow, and hits the other face that encloses A. There is a normal to the prism at 2 at that very point. The light ray then bends away from that normal and emerges from the prism into the air as what we may call the emergent ray. If the incoming light ray were to come along the green arrow, it lands on the right face of the prism as shown. It will bend towards the normal, become the same refracted ray but in the opposite direction and lands on the left face as shown. The new emergent ray follows the reverse of the path of the original incident ray. Thus, we find that both the red and green arrows can represent an incident ray with the refracted ray being the same. We can therefore show all three rays as double-headed arrows. We represent the angles made by both the red and the green arrows with their respective normals as angles of incidence I1 and I2, and the angles made by the two ends of the refracted ray with the two normals on the two faces as angles of refraction R1 and R2. As you can see, some new geometric figures are emerging in the picture. So the teacher invites children into the discovery of some geometric nuances the picture now presents. So in true geometry style, the teacher adds labels to some important points that emerge. Consider the triangle CFG. In this triangle, the measure of angle C is R1, that of angle G is R2, and that of F is unspecified and unknown. Children quickly point out that CFG is just a triangle and therefore the sum of the three angles must be 180 degrees. Given that angle C is R1 and angle G is R2, angle F is nothing but 180 minus R1 plus R2. Consider now the quadrilateral VCFG. From the previous exercise, children quickly pronounce the sum of the angles as 360 degrees, while the angle C measures 90 degrees and the angle G measures 90 degrees and angle V measures A. Therefore, angle F must measure 360 minus 90 minus 90 minus A or 180 minus A. These two taken together mean only one thing to children. R1 plus R2 is equal to A. That is, the sum of the two angles of refraction is nothing but the angle of the prism. Interesting, isn't it? Let us now move to the next geometric nuance. The red dashed line is the path the incident ray would have followed if not for the prism. The prism causes it to follow the path shown by the green dashed line. The teacher then defines delta as the angle of deviation of the incident light ray by the prism. The teacher then adds a couple of additional labels for new points and asks, how are the angles ECF and BCD related? Children take no time to identify them as vertically opposite angles and therefore that angle ECF is equal to I1. The teacher then asks how much angle GCF is. Children spot it as R1, in which case angle ECG is I1 minus R1. The teacher then asks the children what angle EGC is. Children by now familiar with this question respond saying I2 minus R2. The teacher then points to angle HEG and asks what relationship that angle has to triangle ECG. Children quickly respond saying exterior angle, and with one more prompt, they identify an important learning from their understanding of geometry of triangles. This theorem, which they then apply in this case as deviation delta is equal to I1 minus R1 plus I2 minus R2, which can be rewritten as I1 plus I2 minus R1 plus R2. The teacher then throws a leading question. Where else on this board do we see the measure of R1 plus R2? Children promptly spot it here and identify R1 plus R2 and replace it in the expression for delta as A. If you too found all this by yourself as you were watching, you can, I am sure, imagine the joy the children experience as they discover these treasures through their own hard work. The excitement therefore builds up in the class, just as hopefully yours is too. With all this excitement building up, children now delve deeper on the path of discovery. They have already found that the deviation delta is I1 plus I2 minus A. The teacher now asks them how else they can represent I1 and I2 using the concept of refractive index mu, which they defined as sin I by sin R, and asks if that can be used to denote I1 and I2 in any other way. Children typically start with this and then dig into their grade 10-11 trigonometry, specifically their knowledge of inverse trigonometric functions, to rewrite the expression for delta with I1 as this and I2 as this minus A. For children, this is just a typical functional representation as they have seen in their grade 11 calculus. They see that delta is a function of two variables R1 and R2, but at the same time, the teacher draws their attention to this. So they see that R2 can be written in terms of R1. So they do this and rewrite R2 as A minus R, which implies that delta becomes this. Grade 11 calculus once again tells them that delta has now been expressed as a function of a single variable r, and its variation with r can be studied by finding the derivative of this function delta of r, which they have used to compute slopes or find maxima and minima. So they quickly use that calculus toolkit to find out the derivative as this minus this. From their grade 11 calculus, children know that the function delta of r attains a maximum or minimum at that value of r at which the derivative here is 0. But now, as they see an equation in R emerging in front of their eyes, they smell a new opportunity, something they have been doing since grade 7, solving equations, which now extends to solving equations involving trigonometric quantities. They unleash all the techniques they have built up over the years for this. First, they take the two big terms to two sides of the equation. Then they cancel the common mu on both sides. Then they see the ugly square root terms in the denominator of both sides of the equation and therefore square the terms on both sides. Then they employ the most common trick of all, reorganizing terms. That includes cross multiplying the numerator of each side with the denominator of the other and build a new equation. They continue the reorganization and bring together like terms on the two sides. Terms that multiply 1 on either side form the new left hand side, and terms that contain mu square as a common factor form the other. This helps pull out that common factor mu square and leave only trigonometric functions inside the bracket on the right hand side. Children now dig into their grade 10-11 trigonometry armory and recall this identity in terms of which both the terms on the left hand side can be rewritten. With the common term 1 in each, cancelling, leaving us with this. And then they spot the expression on the right hand side looking suspiciously like this identity that they have been using since grade 7 and turn the right hand side into this. But now they see that the two bracketed terms on the right hand side look like these identities from grade 10-11 trigonometry. So they rewrite them to this much shorter expression. Once again, they see an expression they have seen in yet another trigonometric identity from grade 10 and 11. So they rewrite the right hand side as this. Now we see that the right hand side expression is just mu square or a constant times the expression on the left hand side. So they rearrange the terms once again to rewrite the equation as this. They now go on to cancel the 1 minus mu squared and are left with an equation where the difference of two simple terms is 0, which means that the two terms must be equal. And if cos of 2r is equal to cos of twice a minus r, then it must be that 2r is equal to twice a minus r, which in turn means that r is equal to a by 2 or half the angle of the prism, which further means that r1 is equal to r2 and hence that I1 equal to I2 is equal to say I, which if we substitute in the equation delta is equal to I1 plus I2 minus A, we get delta is equal to 2I minus A, which actually becomes I equal to A plus delta min by 2. With this, we are now in a position to write the refractive index as required. What is left is to prove that this turning point is a minimum and not a maximum. Children eagerly and readily do that too and confirm that by computing the value of the derivative function we obtained at r equal to a2 and confirm that it is indeed a minimum. Thus you see here that children following the path of discovery, as we do at Tatva all the time, would have discovered by themselves through a lot of thinking and hard work that intriguing declaration that all other children are forced to accept as truth solely on the authority of their teachers and their textbooks. They do this with the use of their developing faculty of reasoning. All the mathematical knowledge required for this is well within their reach given the grade they are in when they make this discovery. It is certainly well within what one would call the syllabus for these grades. Every such intensive use of the faculty of reasoning only strengthens that faculty, makes such exercises easier the next time around, and enables great feats of thinking by the children in their future. Thus, we see the vast and incomparable superiority of the path of discovery over the traditional and conventional approach of explaining the contents of textbooks clearly, which is what the vast majority of children are burdened with. There is no comparison on the question of the extent and depth of the development of the children's thinking faculty that the path of discovery fosters. If you want your child to be educated in a manner that his or her human faculties are fully developed thanks to their educational experience, you may now know what you should seek for your child. The only question for you to answer to yourself would be,
I hope this video has given you a very good picture of the beautiful educational experience that we at Tatva are creating for every child. If you want this experience for your child and you want to explore how to bring it to your child, all you have to do is to walk into our campus. And you can start that by visiting our website given out here. We look forward to seeing every one of you at Tatva soon. Thank you.